Hey everybody,
Hi.
just gonna give everybody a hello. Welcome to STEAM Camp at the Tesla Science Center with help from the Spur. How is everybody today?
I can.
Got a connection?
I want to be.
Excellent.
Excellent.
So, my name is Steve, and I'm very excited to be here with you guys today. We're gonna have so much fun building and playing with our own rockets right from home. Yes, you will make a working rocket today, and we'll do it with simple materials right from your home. So we'll go over a couple ground rules to start off with, and then we'll go over some supplies that we should all have handy. And then we'll talk about the day and a little bit about rockets, and we'll get right to work. Sound good? All right. Well, we have so many friends with us today, so many engineers that are going to have fun. I want to ask you all to start off by grabbing a piece of paper or an index card and writing your name nice, big, and clear. I'll show you an example. By the way, my name is Steve, and you guys can come check out STEAM Camp workshops with me every week by signing up at the Tesla Science Center. So the reason I would like everybody to have a name is because rather than just raise your hand when you want to share with everybody, it would be a great idea if you held your name up to your camera and I could see you and call just like Charles did. Very good, Charles. That's perfect. That was nice and clear. Vivian, excellent job. Thank you. Aurora, I see you in California. I see Alistar. What a great name, Alistar. Did I pronounce that right, buddy? You can give me a thumbs up. No? Okay. Do you want to unmute your microphone and how do we say your name, buddy?
William. Alistair.
Alistair. Got you. Okay, thank you so much. I see Brody, Vivian. I see Ian Perez. I see Colin, Alistair Jackson, Aurora in sunny California, and Vivian has a great t-shirt today. She's wearing a NASA shirt. I didn't wear my NASA shirt, even though I love to on rocket days, because NASA is known for our great rockets. My NASA shirt is very white, and it's kind of a little glary on the camera. So, all right, guys and girls, nice job with your names. Oops, I'm upside down. There I am. All right, so rockets. Rockets have been around for so long, back to some ancient stories from the Greeks in the year around 400 BC. It's for over 20,000 years. We've been as humans studying and trying to get this thing that would propel really fast with some kind of force. And I would say about 8,000 years ago, the Chinese finally figured out, with all of our, creativity and knowledge, how to get an explosion inside a tube to shoot out one direction and thereby force the object, in this case a rocket, to go in the other direction really fast, faster than they could throw an arrow or shoot it with a bow and arrow or a catapult, because the explosion's force was so great it equaled the force of the rocket. And they used it, I believe, in the year 1232 in a war against the Mongols. And boy, did they surprise and defeat the Mongols with the invention of the rocket. But anyway, at home, we can have so much fun with STEAM, science, technology, engineering, art, and math in playing with rockets. So I'm going to go over a couple supplies that would really help you guys build your own rockets from home today. So instead of using an explosion like the ancient Chinese did, we're going to use a different form of energy, and we call it air pressure, or pneumatics is another name they call, the science of using air pressure to get things done for us. And the reason I like air pressure for this workshop is because no matter what supplies you have at home, everybody has air pressure right inside their bodies. Inside my lungs, if I take a deep breath, I built up air pressure inside my lungs, and when I release it, I have energy coming out. So if I use the pneumatics of my body and grab a simple tube, maybe like a straw, but don't act so quick because this is just one example that you can use today. And on top of that straw, say I build myself my own rocket made out of simple supplies at home. And I'll show you guys how to make all of these simple rockets, but I just want to show you an example. If the delivery system I have, I'm going to call this my launch pad, because I'm going to transfer my air pressure from my body through this tube and create an air pressure buildup inside this paper rocket that I built. And I'll show you how to make these, so don't worry. Just watch for now. And I slide my little rocket over my air pressure delivery system. And if I blow hard enough, my rocket will shoot up into the air. Pretty cool, right? Now, I only gave my air pressure, my rocket, a little bit of air pressure just so you guys could see on the computer screen. But if I really gave a lot of pressure from my lungs, trust me, this rocket would have shot right across my room, maybe hit my ceiling. So these rockets can go far if you build them right. So let's talk about how we build up that force from air pressure into an object that will shoot it off the launch pad. The key is this. When you blow into the object you want to shoot, you don't want any air to escape your rocket except through the very bottom where your tube is going to go, because you want all of that air to build up inside here but have only one place to go out, and that is the bottom of the tube. So instead of using a straw, because some people might not have a straw, what I'm going to do for you now is I'm going to demonstrate how we can make an air pressure rocket with just paper. But if you have other types of tubes at home, use your creativity. Your imagination is key when we're acting like engineers. You can use any types of tubes you have laying around the house. You can use old paper towel rolls. I even have a copper pipe here. I could use this, probably not as my rocket because it's pretty heavy, but I could use it as an air delivery system if I wanted to. Other things you could use that will get a little bit more advanced after we practice our lung air pressure. Later, we could turn this into its own launch pad, because just like lungs, air can fill up this container, and if I use mechanical force hard and fast enough, and I get a tube on top of here, like a rocket that fit nicely on here, it could launch just with me clapping my hands instead of blowing the air out of my lungs. So for now, let me just work with paper, and I'll walk you guys through how to make one tube to deliver air pressure and one tube that will turn into a rocket. Okay, so I'm going to pan down my camera right now, and you guys can follow along with me if you kind of feel like you know what you're doing, or you can patiently just watch exactly what I'm doing in the demonstration and then start afterwards. Okay, so I'm going to basically just need here a scissor, some tape. You can use any kind of tape you want, guys and girls, except I like to use this clear tape because for a rocket, it's smooth, okay? And it won't cause a lot of friction. We don't like friction with rockets because we want them to slide freely on their launch tube, and then we also want them to cut through the wind with as little friction as possible. So a nice smooth tape is good, but you don't have to have any particular type of tape. Okay, and then just paper. You can have white paper from the printer, or you could have, you know, attractive construction paper if you want. So let me pan down and show you first how to make your air delivery tube. That's the one that you will blow through, okay? And that's if you don't have a straw or if you want a bigger delivery system. So let's scroll down here, and all I'm going to do is roll up a piece of paper and then tape it. But I want to make sure my roll is nice and even on both sides. Take my time. I don't want to rush this because I want it to come out nice. And remember, since this is going to be delivering air from this side to this side, when we tape the paper roll, we want to seal the entire seam. So I'll show you what I mean by that. I'm going to take my tape, and I'm just going to get a little piece at first because I want to hold still my tube. Now, once I have that, I'm going to go to the edges so those don't move. See, I already got a kink in my tape, so that's okay, because when we engineer things, everybody, we always mess up the first couple times. That's why it's so fun, because we always have room for improvement, and we could consider this a prototype. A prototype is like a beta version. If any of you guys play video games or know when a new game comes out, the new release is usually called a beta version. And that means it's kind of like a practice version. So when engineers make a practice version, they call it a prototype. So this is going to be our prototype rocket, meaning it doesn't have to look so pretty. We just want it to work and have the basic parts. So if you noticed, I took my tube here and I sealed the entire seam so that no air can escape except outside one end. So when I blow in this end, no air is coming out of the seam. It's only coming out here. And you can test it. I can feel it, so I'm happy with this. Now, you want to build the tube for the rocket itself. This is a little tricky because now we're going to deal with geometry and math and diameters. The distance across from this tube has to be able to fit inside the rocket tube. So a good way to do that is I'm going to use a different color paper so you guys can see. So if I want to make sure this tube is skinnier than this tube is going to be, here's a secret trick, everybody. Just use this tube to roll this paper around and make sure it ends up a little bit bigger, like so. So again, I'm making sure it's nice and straight, and I want it a little tight around the white tube, but I don't want it super tight so that we can't move. We want this to be able to move. Does everybody see that? We want this to be able to move, but we don't want this circle to be too much bigger than this circle, because we don't want a lot of air escaping this purple tube. We want a small amount of air to be able to shoot out of here with a strong force. Okay? And I'll show you the difference if I did not have a tight tube around the white tube. All right, so now the same thing as before. I'm going to tape my purple tube so that no air can escape that one either. Starting off with a small piece of tape. I go on both sides. Now, again, you guys do not have to be keeping up with me right now because I will be available to give you one-on-one help if you want to just watch me now and then work together on this. So here's my big piece of tape. I'm going to make sure I seal this entire rocket seam. And then I'm going to show you one more very important tape job you have to do on the rocket piece. All right, so I have my purple tube sealed on the seam along the whole tube, but very important, boys and girls, pay attention to this piece, okay? I do have 2 tubes that successfully slide back and forth, but I have a problem with my purple tube because if I blow in my white tube, all the air comes right out the top of my rocket, right? So now I want to tape the top of my rocket tube so no air can escape the top. And that's real easy. I can just take my tape and go over the tube like so. Now, if I look around, just give me 1 second. I'm going to get some masking tape so you guys can see a little bit better. Okay, I'm back. So now, just so you can see, I have the white air tube and then my rocket tube. On the top of my rocket tube, I want to seal off the top so no air can escape there. And then after this, we're not going to make any more part of the rocket. We're just going to see if we can get this purple piece to launch off the white piece. And I'll show you what I mean exactly. Okay, so I have a nice seal here. I don't see any part of my opening. And I have some nice action here. And I don't have a lot of space in between my tube. And I'll show you why in a second. But let me test out my prototype. Does this work? Everybody watch. Oh, it worked. Okay, I'm happy. But let me show you what happens if my rocket tube is too big for my launch tube. Like this, for example. Okay? Who can tell me what they think would happen if I tried to launch this tube? I see Evan with his hand up. I'm not sure if that's your name or one of your parents, but Evan, if you can unmute. Okay, great. Evan, what do you think would happen?
I think that the air will just escape from the bottom and that the cardboard tube won't lift off.
Okay, stay unmuted for me a second, Evan, because you're very smart in your statement, but I want to clarify. So you're saying that it won't launch, basically, because the air will escape the bottom. However, the air in my working rocket also escapes the bottom. So what's the difference?
The cardboard tube has more of an open space, so the air will just go around the launcher and just exit. While the other rocket, the paper one, has barely any space, so it's forced to lift off because the air is basically trapped inside.
Very good, Evan. Thank you. Your key word there was force, okay? Since so much air is trying to escape this small space at the same time, the force builds up strong. But you used a great word too, describing this bigger tube. It kind of just exits this way, which is very accurate. It's kind of like if I just exhale my lungs into the open air. Air kind of flows out wherever it's going to go, just like this. It kind of just spills out. So no air pressure is building up. It doesn't really have a chance. Evan, that was great. Thank you for participating, man.
Thank you.
So I want to see, before we add other parts to our rockets, who can just simply get one tube to launch another tube like this. Yes, Aria.
Can I show it?
Yes, please show it. Make sure we can all see in the video too.
When you stand back a little bit.
Oh, I saw it, Aria. Excellent job. So who else wants to? Oh, Colin. Great. Thanks for holding up your name, buddy. All you have to do is unmute your camera. Or microphone, I should say.
Can
There you
I show my rocket too?
Please do, Colin.
Almost.
That's okay. Excellent. Now, one of the things we like to do, Colin, when we engineer things is identify things that could be improved. Now, I love how you persevered. You showed grit because on the first test, something didn't work. But that always leaves us an opportunity to learn. And that's why I love being an engineer, because I make most of my learning through my mistakes. So, Colin, what did you notice in your prototype that was holding up its function the first try you tried versus the second?
Maybe the top of the rocket, the tape might have got stuck to
That's a great point. I think you're accurate on that. So what do you think we could do to improve our rockets in that case?
We could put like a piece of paper at this end, so then it would still be covered, but it wouldn't get stuck to this tube.
Spoken like a true engineer, Colin. Excellent job. Okay, I see. Is that Noah? Can I see another person's name and we can watch your prototype go? And then I want to show you how to add two important parts to our rockets. Anybody? Alistair, you're up, buddy. Make sure you unmute your microphone, please.
So, I originally tried to wrap this straw in paper, but it wasn't working out that good. So I decided to try to take out like the part that holds the lead and take out the lead in it.
Yes.
And I could put the straw through so it'll be good at launching.
That's awesome. And you could probably even seal the top with just the pen cap, right?
What I did is I put some hot glue on the top.
Perfect.
So air would escape.
So did you test it out yet?
No, I'm still struggling to get the bottom out.
Okay. Put a little elbow grease in there. Maybe you have some pliers around. I'm not sure, but that's a good idea. I've made many rockets at home with the tubes from pens or markers. Like this one here, I could take apart this pen and it would serve as a great tube. I just noticed somebody else had their hand up. Jamie?
No, I didn't.
What are you trying to get out?
Entire like
Jackson. Hi.
Oh, hi, Jackson. How are you?
Great.
Awesome. What do you have there?
Oh, what? Just.
Let's see. It worked. Excellent.
Oh, yes, it did.
You know, I am never more happy than when I'm in a room full of awesome, fun engineers. So this
Okay,
is
yes, it goes this way.
so. I want to take a quick little break and talk about Nikola Tesla, the guy, the inspiration behind the museum we're all here together with. Nikola Tesla was a futurist, a visionary, and he would be so excited 100 years later to see us all working with these rockets. One of his major inventions and contributions to human society was the remote control technology. In 1898, he introduced the first remote control robot. It was actually a boat that operated. right in New York City, actually, to a fair for electrical engineers. Everybody was amazed. They thought he was magic. They thought he was doing some kind of tricky thing and fooling everybody, that he was actually operating a machine from far away. So how that relates to rockets is, these days our very advanced rockets are controlled remotely with remote controls and GPS systems. So he would be so proud to see us working on this today. Which brings me to a very important part of our rockets, and that's called the fins. The fins steer a rocket through the air. It determines the rocket's flight path. And why is that important? Well, because although we don't have remote controls, the way you position or shape your fins today is going to determine if your rocket flies straight, or do you want it to turn in its flight path, or if you're really skilled and you play around enough. Again, engineering, we're always testing new ideas, messing around with different designs. Some people can get their fins shaped so that your rocket can spiral. But let's just start with basics for now. I'd like you to take your prototypes and add a couple fins to the bottom of your rocket. Now, I'll show you an example of how you might be able to do it, but you don't have to follow my idea. What I would suggest, though, is that you choose a number of fins to use, maybe 2, maybe 3, maybe 4, whatever number you want. But when you do put them on, I suggest trying to evenly space them out around your rocket so that you have a symmetrical distribution. I will show you a basic way you can make a simple fin. I'll just make some triangles, and I'll show you how I would put them straight up and down if I want my rocket to fly straight. Again, pick your shape, pick your number of rockets, and your angle as well. So let's pan down again. I'll show you a simple way to make some fins. I can, if I want, all I have to do is really cut a triangle. And I could add a fin to the bottom of my rocket like so. But I think I want to make my fin a little bit stronger than a single sheet of paper. So what I'm going to do is I'm going to cut a square or a rectangle, something four-sided, and I'm going to just try my best. Remember, this is just a prototype. I'm going to try my best to get it with 4 equal sides. And then if I fold over into a triangle, yeah, I have a little bit extra here. That's no big deal. I'm just going to fold that over instead of cutting it off. Now, what I've effectively done is strengthen my paper. It's a lot more sturdy than just one flimsy sheet of paper. So I'm going to go back to my handy dandy tape, and I'm going to tape it onto my rocket. In my case, I feel like putting on some straight fins. So I'm going to do my best to line up my fins straight on the rocket. And a good way to do that is, well, I happen to have a line on my workspace here. You can use that, or you can use many different things you have laying around. For example, say you have another tube nearby. Check this out. I can take a pen, or let me use a marker so you guys can see it a little bit more clearly. And I can use another straight object as a guide for a straight line. And if I push my 2 tubes up together, and this doesn't have to be tubes, I can even use a ruler if I wanted to, okay? But I just happen to see this tube laying here, and I like it because if I use it as a guide, I can basically give myself a nice straight vertical line that if I tape my fin right along that, I know I have a nice vertical angle to my fin. And I would do it just like this. Now, for me, I personally think it would be smarter if I also put a piece of tape on this side of the paper. So that's what I'm going to do. You don't have to, but it will make it stay in place a little bit better. So I'm just going to go ahead and do exactly that. And since I folded my fin an extra time, I don't like that flap. So I'm also going to tape that. So why don't you guys go ahead and come up with your own fins, and we'll all come back together and share our results. If you happen to get done with fins, please hold your name up or raise your hand, and I'll call on you for you to share with us. Hey, Colin, what's up, buddy?
I made these shape fins. I think they'll work good.
Oh, I love it. I think so too. Now, that looks like it's a little bit more sturdy than regular paper. What are you drawing on?
Cardstock.
Cardstock.
Very good. Cardstock is great to work with this project. It's stiff, but it's very malleable, meaning we can move it into different shapes easily. But it's stronger than regular paper. Kind of like an index card. Excellent. So, remember, fins have the purpose in rockets of what? Who can tell me why rockets have fins? Anybody? Alistair, you have to unmute, man.
To control the flight path.
Very good. Exactly. It's like the steering wheel of a car. This is how we steer our rocket. Next, we're going to talk about what goes on top of the rocket. I wonder if anybody knows what the name of that is. It's the pointy part that goes on the top of a rocket. In this little mini example, I just used a pen cap, but I'm going to show you how to make one for this with paper. Or if you don't know the name of this piece, I wonder if you know why we use the piece, why the rocket relies on it. Yes, sir, up top, is that Noah? Hey.
Is it a cone that's on top?
It is a cone. For some reason, when we talk about the cones on a rocket, we call it a nose cone. Nose cone. I guess because it's the nose or the front of the rocket. What about, Noah, do you have any idea why we would even want a nose cone on the front of a rocket?
Is it to make it go faster, like cut through the air faster?
That's exactly right. That's its only purpose. So can you guys all imagine driving in your parents' car? Has anybody ever put their hand outside the window and held it like this? Yes, I see somebody with their hand up. They did. And what happens when you have your hand like this? You guys can unmute.
It blows your hand back.
Right. That's because of wind resistance. Now, unmute again and tell me what happens when you turn your hand like this.
The air goes past you.
Yes,
and it doesn't push your hand.
Right, because we made it more like a nose cone. We made it more aerodynamic, and it's able to cut through the wind a lot easier than when your whole hand is catching all that wind resistance. So, when you are done doing your fins, I'm going to show you how to build a nose cone. Yes, Alistair. And then Jackson, I'm going to come to you.
So I finished making my cone. Can I show you how it flies?
Please do, definitely.
So the straw wouldn't fit. It was too tight. So I found something in the pin that would work. And later, so there's some holes in there. So later I'm going to take those over. And
okay. Let's see. Oh, nice job, Alistair.
It wasn't that good, but I'll try to improve it.
Yeah, it looked like the rocket itself had a bit of weight to it, because what I observed was it dropped pretty quickly. So the more force you can get in air pressure there, the faster or better it'll fly. Good job, though. Jackson, did you have your hand up, buddy? No? Okay. All right, so, yes, sir, with your hand up. I'm sorry, I don't have your name, but feel free to unmute. Hey, guys, what's your names again?
Colin and William.
Chloe and William?
No, Colin and William.
Colin and Will. Oh,
William.
Colin and William. I'm sorry. Okay, what do you guys have there? Ooh.
This is my rocket. Mom, I can't make these sized right.
Those fins came out awesome. You did them nice and symmetric, you know, evenly spaced around the body tube of your rocket.
Our mom did it.
Oh, Mom. Okay. Well, guess what? Next time, okay, well,
Give me another of these.
Mom can hang out with us anytime. She's a great engineer. I'd love to have her company. So, let me show you how I can build a nose cone. But remember, like Noah said, it's just really a cone. So if I have something that's shaped like a cone, I could just use that. But if I don't, there's another way we can roll paper so that it forms a cone instead of a tube. So I'll show you that right now. Pan back down to our work surface here. Okay. This time I will use white paper because my construction paper is not as strong as the white paper, and I kind of need a little strength here when I do this roll. I want to roll basically a cone, and the way I do that is where I start my roll, I keep it really tight on one side and really open on the other side. So it's almost like a spiral. And if you watch, once I started, it's easy to just continue. I keep this side nice and tight, try not to let it move at all, and I just roll the big wheel like so. And then when I get to this part, I want to keep this clamped to here with my fingers. So I want to try and make a sneaky move here and keep holding it. And then I pick it up and I have this seal here. I mean, this seam that I have to seal. So I grab my trusty tape here. Get this nice and tight so I can not worry about it unraveling. And voila, I have the makings of a cone. Now I can let go and I can really make sure I tape this a little bit nicer now. And that's exactly what I'm going to do. I'm going to follow my seam as best I can with the tape. I'm not too worried because, again, this is a prototype. And when I'm done with this rocket, I'm going to make a much nicer one where I consider how good it looks. And when I move on from my prototype, I want to improve the function of my rocket. Alistair, it looks like your rocket's taking off much better now. I wonder what you changed. Go ahead.
So I figured out there are holes in there, so I taped over the holes.
I was going to say that. I remember you mentioned that the first time. There was some kind of tube inside the pencil, and you said it had holes in it.
Yeah.
So what was that tube for? Was it to hold the lead in the pencil? Is that what? Yeah, okay. All right. So watch this, everybody. Now I have this big cone and this relatively small rocket. So how do I turn this into a good nose cone for my rocket? Well, I want to cut my cone as close as possible to the diameter of my rocket. And this is a good way to do that. I can stick my rocket right in the cone and I can kind of feel it with my fingers. And I can tell that right about here is where my rocket tube ends up. So I'm going to make a little pen mark here. And I'm going to just try it out. I'm an engineer. I'm going to try it. So I'm going to take out my rocket and I'm going to cut with my scissors what my best guess was to match the diameter of my rocket, and then we'll test it and we'll see. And who knows, maybe I'll have to improve my idea if it doesn't work. So this is what I ended up with after I cut it. Now let's just see. So I have my rocket, and you know what? For a prototype, I'm very happy with this fit. Okay, it's not perfect, but it is very close. And it will definitely help this flat rocket surface that's going to catch a lot of wind and slow up my rocket. It's going to help my rocket. Now look at the shape difference. Now I have a very pointy front that will cut through the winds or the air resistance. So that's what I'm going to do. I'm going to tape my new prototype nose cone to the top of my rocket. And then I'm really going to see if this thing flies. So I'm still so excited about how proud Nikola Tesla would be to see us all working on rockets, because not only did they take his remote control invention and really get rockets to steer better with them, but now going from the year 1232 with the ancient Chinese using rockets, now we're reaching the planet Mars with rockets. We're getting out into space and then using a lot of rocket technology to travel across our solar system. And like I said, Mr. Tesla was a futurist, and he would be blown away like a rocket to know that we have made it to planet Mars. So cool. So I see in my videos some great rockets coming together. If you have anything that looks close to this, you are doing a great job, everybody. And I see many rockets out there that are much better than what I have here. That's excellent, Ben. Thanks for the 3D effect. Do you want to unmute and talk to us about your rocket?
Yeah, this is Charles.
This is Charles. I'm sorry, Charles. Is Ben daddy maybe?
Yes.
Okay, Ben and Charles, what do you guys have going on there? It looks like a really nice design.
Thank you. So I put on the four the triangles fins. So and I kind of twisted them like this, so it might spiral.
Oh, interesting. I love the exploration. Okay. I wonder, you might have to describe to us the flight, because it looks like a good rocket's going to shoot right out of the camera view, but do you want to give it a go?
Give it a shot. Shoot it out of the ball and see how it works.
Let's see.
Oh, blow it.
Oh, right.
Blow it like you mean it.
Okay.
Yeah.
All right, all right, all right. Looks great, man.
Thank you.
Now, what you want to do here, Charles, is remember this is a prototype, and ideally, after class ends, if you're really having fun with this, I encourage you to make another one. And while you're making it, number one, naturally, it's going to be a better one, because inside that wonderful creative brain of yours, you don't even realize how many mistakes that you ran into and solved without even thinking about it. So number one, your rocket's going to be much better than it is right now. Number two, you're going to actively improve on it by things like, oh, this time when I roll it up, I know I could do it better this time by avoiding that one last mistake. And based on observing how your rocket flew, you'll know if you want to make it heavier or lighter, or you want to get that tube to be more forceful, or you can even consider changing the angle of your launch and take observations. If you shoot it up straight in the air, how far that way does it go? Usually it just goes up more than far. And then you change the angle and check out which angle equals the furthest distance. There's so many things you can do to improve these rockets, make them look better and make them function better. So cool.
Thank you.
Okay. Let's go to somebody else with their hand up. We have Colin again, right? No, I'm so bad. I'm sorry.
William.
William, I'm sorry, William. Go ahead. What do you have?
A rocket.
Awesome. Does it work yet?
We haven't tested it yet.
All right, let's get that test going and check it out.
Okay, so you want take that out in the middle. Take the middle tube out. You can't hold this part. You have to hold the bottom.
It's just gonna slide.
Here, watch. Try. Ready? Blow it. Hard. Blow hard. Put your mouth over the whole thing. Oh, do it again. Do it again.
I
Do
see
it
it.
again. It was moving. Try again. Try again. He's waiting for you. Hurry up.
It's okay. Take your time.
Can I try?
No.
No?
Okay, guys. Well,
All
if
right.
you want, definitely come back and we'll check it out. So, believe it or not, we are down to like a little less than 15 minutes in class. So I definitely want to have everybody in class share. But while I wait for you to get up the nerve to put up your hand and share with us, I want to show you how to make another launching system. And I'm going to show you how to avoid using your lungs. And now we're going to get some air pressure out of a recycled water bottle. First of all, mine's a little crunched up, so I'm going to transfer air pressure from myself into the bottle. Okay, now I have full capacity to fill in air here. Now, you guys all saw me build this prototype rocket, and while we were talking, I said to myself, let me just check if it fits on a water bottle. And guess what? I got really lucky, everybody. My rocket happens to fit right over this water bottle. So I get to show you a really cool demonstration now. So there's a big difference when we work with air pressure. Do I deliver my air pressure slowly and steadily, or do I deliver my air pressure with a lot of quick force? And that will make all the difference. Noah, I see some great action going on over there. If I give my rocket some quick, strong force, it should fly up. But watch the difference. If I don't deliver that air pressure in quick enough time, I'm really gonna get nothing. But if you watch this, and I'll try to back up my camera so you guys can get a nice view of this launch. You can see the top of my rocket and my ceiling. So what I'm gonna do now is I'm gonna take my hands out like this and smash them really quick into my water bottle, and you guys can see what's gonna happen. You ready? 3, 2, 1. Oh, very cool. Did you like that, Aria? I see you having a great time. Okay, Colin, come back to us. I see your name up. Just unmute your microphone, buddy. Colin, you have to unmute your microphone. We can't hear you. There you go.
You can put the balloon in it, and then you could wrap it on the edge, and then you
Whoa.
could blow into it.
Check it out. Can you show us?
I can't blow up the balloon.
Oh, okay. Let me ask you, why do you think it won't blow up?
Mom, no. Mom, can you do it for me? Can you do it?
It won't work.
Mom, yes, I will.
Why do you think it won't work?
I don't know.
Well, I'll tell you why, because that balloon wants to expand when you're blowing into it, right?
Oh, I think I know.
Why?
Because there's air in the bottle, and when you blow it into the balloon, the balloon will get bigger, and then there's no space for it to blow up.
Pretty much.
I know.
Go ahead.
Because the air is not letting the balloon blow up because it's pushing on it, so it won't blow up.
Very good. You're both right. Basically, what's happening is the bottle only allows so much air in there, and you have a balloon that's trying to expand by accepting more and more air into it, but it has nowhere to go.
I also noticed something else cool. Look.
Yeah, what's up?
If you squeeze the bottle, look what happens.
Now that is cool. Now you're using the air pressure inside the bottle.
And then that's another way to blow up a balloon.
It sure is. You're using different air pressure than your lungs, right? So, let me see. Anybody else has a different launch system? Oh, I think I want to see what Aurora's doing over there in California. Hi, Aurora.
I have my mom actually made this, and she took a balloon and she put this little cap that opens and closes.
Yeah.
From this bottle, and she put it inside the balloon.
Awesome.
And blew it up and closed it so no air could escape, and she put my rocket on it, and then the air went through it and it launched.
Wow, that's incredible. Now, in my, oh, I saw that. That was great. That was excellent. In my mind, Aurora, I'm thinking of an obstacle here. If you get that cap inside the rocket, how do we release the cap while it's in the rocket? That's a new challenge we'll have to get past, correct? Who else wants to join in and share? We have almost about 5 minutes left. I'd love to hear from everybody. I see we have Suhansi. I don't know if I'm pronouncing your name right. We have Vivian still. While you guys decide if you want to share with this, I will go back to Colin and William. Go ahead, boys. And then Aria, you're next. And Brody, you'll be after Aria. So Colin and William, if you could unmute your microphones. Awesome. So what do you have?
So the air from the balloon, I put it on the seltzer bottle.
Yeah.
And then the air can't come out. It goes into the seltzer bottle. Can you show us? When you squeeze the balloon,
I bet you
the air goes all in the seltzer bottle.
Right, and the seltzer bottle will not let that air out of its plastic. So if you squeeze that balloon hard enough and fast enough, I bet you the seltzer bottle will shoot like a rocket itself.
Wait, I think I can do it. I think I can do it.
Make sure that bottle is not facing you.
William, wait, can you face?
William, let me do it. Make it facing up. No, stay up, stay up.
I hope you guys come back. You're a lot of fun to engineer with.
Want me to do it?
Well, if that balloon is really wrapped tight around the bottleneck, it might be really hard. So I'm gonna come back to you. So okay. You guys are going to invent some great things. Aria, do you want to share now? Okay, you have to just unmute. Hey. Oh, you have a bottled action there. Okay, what's going on?
So, I just put this paper on and then I squeeze this like I'm
Let's see.
going to.
Okay. Ooh, good camera angle. Oh, I love it. I love it. You did a nice job. Now, I wonder, are you going to add fins and a nose cone to that? Very cool. And what about Brody? I know Brody was looking to share something. He has a great camera angle. It looks like he's ready to show a nice launch there. How you doing, buddy?
Good.
Awesome. You gonna show us your rocket?
Yeah.
Show the
All right.
base.
All right. So,
On an angle.
yeah, we had a little angle going on there. We're looking for something we call balance. So you're
Show the
gonna
base,
want it.
Jen.
I think I am.
No, you're not.
There we go. That looks like a nice
Oh, I
launch
forget.
pad.
Okay, you can go.
Oh, much better, much better. Now, check this out, everybody. Do you think maybe you could probably generate more force than your hands with a stomp of your foot? But if I was to stomp on a bottle like this, the bottle would have to be laying flat on the ground, right? So now we're talking like the straw did. We would have to have a launch pad that changes the direction of the air pressure. So I would have to build and construct my own launch pad where a tube, without bending it, would redirect, and the rocket itself, which is all the way on the other side of my room right now because I launched it before. Where did it go? So the rocket would have to go on top of this, and then if I kicked my foot down really hard on it, I bet you I would have a great launch pad for a good rocket flight. So we have a couple minutes left together. I really hope you guys had a lot of fun, and you're going to take these ideas and run with them, because the sky is the limit for real when we're working with rocket projects. Let's go to Alistair. He's going to share something before we wrap up, and then we'll go to Evan as well. Alistair? Just unmute. You have to unmute. That's okay. It's easy to forget. That's
Sorry.
all right.
So for my design, I thought of a shark because it can go pretty fast underwater. So maybe it could be like air, so it could go faster.
Alistair, you bring up a wonderful point, because a lot of people, because we can't see air, we don't realize that it has mass, and it is just like water. It's fluid, but we can't see it like water. So a lot of times, like Alistair said, he thought of a shark and how it cuts through the water really good because of its fins. And a lot of times engineers take ideas from nature, like a shark in the water, and develop products or inventions that mimic nature to suit our needs. Thank you so much for sharing that, Alistair. That's a great point. Remember that a lot of our inventions are taken from observing things that happen naturally on our Earth. Vivian, I just saw a great rocket launch there. I would love it if you shared after we go to Evan, you and your NASA shirt. Hey, Evan.
Hi.
Hey.
I just got an idea. What if you fill or put a balloon in your rocket and then blow up the balloon so when you let go, it just blasts off?
That's a great idea. That would definitely take care of the sealing problem, because no air would escape except that bottom of the balloon. However, I think we have one problem, because just like Colin and William tried to do, if I put a balloon inside some kind of canister, the canister is going to prevent the balloon from blowing up past a certain point.
If you blew up a balloon and then attached kind of ropes to it, which attached to the airplane or the rocket, then it would just hold on and shoot.
Yeah, if it was outside the encapsulated structure, definitely. I encourage you, Evan, to go with that wonderful engineering idea, see what you come up with, and if you take a photo of it, you can upload it to the Tesla Science Center.org's website. Okay, if you email info@teslasciencecenter.org, you can send your pictures, and this goes for everybody. Send your pictures of your rockets into Tesla. Again, the email address would be info, I-N-F-O, @teslasciencecenter.org. And if you have a problem finding that, you can go right where you guys registered for the class, and we'd love to share your pictures with the whole world. Okay? Now, I want to remind you guys that we have these classes every week. It was really fun hanging out with you. I love playing engineering, and you guys were all great, and it's always fun to see faces come back. If you have any ideas for projects you want to do in the future or workshops, I can pretty much turn anything into a fun, awesome engineering project. I would love to hear your ideas, and I come up with some great, exciting things to all of us to build them and play with at home. All the while, don't tell your parents, we're secretly learning all this math, science, technology, engineering, and art. In fact, if you like art, everybody loves when an engineer can make something look attractive. So if you redo your rocket, make sure you make it look good. So, again, look at the Tesla Science Center for workshops to come up. Jackson, thanks for showing us your muscles there. Everybody, how about everybody do some muscle strong about their accomplishments today? Evan, good job. All right. Thanks for the great idea. And Charles, excellent. And Vivian, you didn't get to come back and share your awesome NASA rocket, but everybody can see that thing launching away. So I would love to see you guys again. Please check out the website for upcoming classes. And again, my name is Steve, and we are brought to you by the Tesla Science Center and the Spur. It was really nice hanging out with you guys, and come on back.
Bye.
Thank you so much.
Thank you.
Thank you. Bye.
Thank you.
Thanks.
Bye.
Thank you. Bye,
See you
Jackson.
sometime.
Bye, Alistair, Vivian, Aurora. Bye-bye. And Charles and Ben, thank you so much. Suhansi, bye-bye.
Bye.
Rody, take care.
Bye.
Bye, Evan. That's a good balloon there, Charles.
Bye. Thank you.
Bye, guys. Thank you, Alistair. Have a great day. Bye, Aurora.